All right, let's get started. Good morning. I think week 2 Tuesday. We're already 5 lectures into the class. We have been seeing two's complement, binary addition, subtraction, multiplication, and then we moved on to Boolean algebra. And today we're going to continue our conversation on Boolean algebra, and then I'll show you some of the canonical representations of Boolean functions in terms of minterms and maxterms. So here's today's agenda. I'm going to start by reviewing Boolean algebra and then providing you with more examples. I read some of your feedbacks from week 1, and many of you are looking to see more examples in lecture. So here they are. And then we'll see how to represent functions in a generalized sum of products, or like a specialized sum of product and product of some forms, which are called minterms and maxterms. And finally, we're going to deal with incompletely specified functions, functions which have some input patterns that are known to never appear. So a couple of words about the upcoming midterm. So midterm is Tuesday next week, Tuesday of week 3. And it's going to cover everything until the end of this week, so until this Thursday. So next Monday is going to be like a review session, no new material. And then the exam will be open note. So you can bring as many pages as you like, your own notes. You can now bring lecture slides, no textbook, and no workbook. So anything that is your original work, whether it's handwritten or typed or printed, whatever you like, you can bring that into the exam. And the exam will focus on conceptual understanding rather than mechanical tasks. I wouldn't just give you like a 10-bit binary number and ask you to do multiplication. I wouldn't give you like a 10-digit number and ask you to show me x is 3 and do addition. Right? That will not happen. This will focus on conceptual understanding. Roughly the same level of conceptual hardness as some of your workbook questions. So here's how I look the interaction between lecture and workbook and exam. So lecture is essentially showing you somewhere in the middle of the hardness, conceptual hardness level, and in the relatively low end of computational efforts. In the workbook, you have some calculation questions where you need to do quite a bit of calculation, a lot of additions, subtractions, multiplication. But that's just for you to practice the fundamentals. Right? Also about Boolean algebra, you saw a lot of practices about manipulating Boolean expressions on Monday's workbook. Those are just for you to learn the basics, and you have to go through some of those practice to just get to that baseline understanding level. The workbook also has some of the more conceptual and creative questions. Right? They sometimes go a little bit above and beyond the lectures to drive a new concept, right? And drive you for the fundamental understanding of the material. And the exam is somewhere sits at the bottom right side of this trade-off space. Conceptually, it's going to be medium to hard level, but that is assuming that you have already learned many of the things through the workbook and through the lectures. And computational effort is minimal, so do not even attempt to solve these questions in a brute force method. It's going to be very time-consuming if you try that. So we really hope you can conceptually understand the topics and then understand why things work the way they do. And with that understanding, this question should be solvable with minimal computational efforts in the exam. Yes, Rona?
Is it going to be similar to the creative?
Not exactly. Again, the creative question, sometimes you're driving an entirely new topic with multiple parts. And in the exam, all of the questions will be single-part question. And they're going to be concise. Right? So I would say they are similar to the weekly synthesis question from last Thursday's workbook. The last 3 creative questions from Thursday, those were previous exam questions. Some of them actually the more difficult exam questions from the midterm. So you can expect the midterm question to be slightly easier than those weekly synthesis parts.
And is there an official practice?
No. I can share you with some of the thing is, I'm always developing new questions for the midterm. And I can share you some of the scrapped questions, the one that we drafted but decided to not include in the midterm. I'll share you with a document that tells you the topic of every question in the actual midterm exam, and also some of these questions you can use for practice. But do not call it formally a practice midterm. Right? Yeah. Any questions about this? Yeah. All right. So with that, I'm going to show you more examples of Boolean algebra, just to complete our conversation about Boolean simplification. All right. So here I just have, here I have 4 Boolean expressions. Each of them is not minimal. And we can apply some of these axioms and theorems that we learned from the last lecture to simplify them further. So looking at the first equation, top left, is there any simplification opportunities that you observed? You can factor out a, b, and d naught. That's exactly right. So a, b, and d naught are shared between the two terms. So you can factor it out. Then write it as a, OK, let me use a thicker pen. A, b, d prime times c plus c prime by applying distributivity. And c plus c prime by complement is just 1, so you get a, b, d prime times 1, which is a, b, d prime. Or you can also say I just apply the uniting theorem directly to those two terms, and then I'll get a, b, d prime. Right. What about the second example, top right? Right. Any room for simplification that you can see from that example? Right. That is arguably a little bit more complicated than the first one. Any ideas what we can do to simplify it? Right. A hint, you cannot get rid of like some of the terms entirely, but you can get rid of some of the literals, right? Some of the variables from those terms. Right. So in general, to apply these Boolean theorems, you might need to do a bit of manipulation and distributivity beforehand, so that basic form of the theorem shows up. So what I can do is, for example, I can take a look at these two terms. They have a prime in common, right? So I can factor out a prime, b plus b prime c prime d prime, plus a b c d prime. Right, now if you look at this part of the expression, right, b plus b prime c prime d prime, that should remind you of the term elimination theorem. Right, that theorem is saying that x plus x prime y equals x plus y. So essentially, this x prime can be eliminated when you have a larger term containing its complement. Right, that's exactly what we got in that sub-expression. We have b and then b prime. B appears like a large term. B prime appears as a literal, a smaller term. Therefore, we can get rid of b prime. And that allows you to get the expression of a prime b plus a prime c prime d prime plus a b c d prime. I'm skipping the steps a little bit, right? But you see the idea, getting rid of the b prime and then applying distributivity. You can do a little bit better by also look at these two terms. They have b in common, and then the a variable appears on a prime on one side and then a non-complemented on the other side. So what you can do is you can sort of factor out the b plus b c d prime plus the middle term, a prime c prime d prime. Oh, sorry, here should be the variable a. And then when you look at this part of the sub-expression, the complement of a prime appears as a literal in that product term with 3 literals. So again, we can get rid of this a term, or a literal. And then you ended up getting a prime b plus a prime c prime d prime plus b c d prime. Essentially, based on the original expression, we are getting rid of this b prime, and we're getting rid of that a. Right. And after you have practiced this for a little while, you can essentially see that right away rather than showing these detailed steps, and that's perfectly fine. Right. Be able to essentially quickly ignore the a prime and then observe the relationship between b and b c prime d prime, and then get rid of b prime directly. Right. Yeah. Any questions about these two examples? Okay, then let's move on to this one. What about this one? Yeah. Anything that you think we can? Well, this is similar to the first example, right? You have this AC that is shared in common between these two terms. I have B over here, B prime over there. So those two terms can be united, which gives you AC times B prime plus B times A prime BC, which is AC plus A prime BC. And then this is, yeah.
No.
Go ahead, no, go ahead.
I was going to say you can factor.
Yes, you can factor out C again and then apply elimination. So let's try to do that. C times A plus A prime B. And then you can get rid of A prime, which gives you AC plus BC. Right? AC plus BC looks indeed quite minimal. That's pretty much the minimum you can get. You could say that you factor out C to make it like C times A plus B. But between these two representations, it's hard to say which one is minimal. This is a two-level sum of product expression. This is a two-level product of sum expression. Right? So these are just two alternative forms. And in general, we really cannot tell which one is more optimal. So you probably want to try both, and by the look of it, that product of sum is a little bit more minimal. So you can call that the minimal expression. Right? This one requires 3 gates, an OR gate and 2 AND gates. This one requires only 2 gates, an AND gate and a single OR gate. But you see, you can approach this Boolean simplification using different theorems, but they will also take you to the same result. So let me try to apply a different sequence of Boolean expressions. So the other way to make essentially the same proof is, what I can do is I'll duplicate ABC. E plus ABC plus ABC plus A prime BC. I can do that because of idempotency. X plus X equals X. And that applies when X is an expression. Right? And now these two terms can be combined into AC. These two terms can be combined into BC, right? Which gives you the very same result. You see, I'm applying a different sequence of Boolean algebra, and I ended up getting the same minimal expression. So it is quite flexible. You don't have to really follow any strict sequence of steps. There are multiple sequences that will take you to the same result. All right. So, and then the last example, bottom right. Any ideas how we can simplify that expression? Right, that Wx and Yz expression. What can we do? Well, these two terms look kind of different. Right, they look quite different. I don't see any opportunity where we can apply term elimination because they just look too different. Right, in that scenario, typically what you need to do is to apply consensus. Consensus allows you to add some quite different looking terms, but maintain the equivalence of the expression. So what kind of consensus term can I do? Well, I need to look for my pivoting point or the anchor point, right? A variable and the complementary variable that appears in two terms. I'm seeing x and x over here. Sorry, x and x prime over here. And therefore, what I can do is I can add in this additional term of wz prime to my expression without changing that function. Right? That function with 4 terms is the same as this expanded function with 5 terms. And now if you consider wz prime with some of these original terms, wz prime is strictly larger than wy prime z prime. Right? And by absorption, I can get rid of this wy prime z prime. Right? Absorption saying that a plus ab equals a. Right? I have a larger term with fewer literals and a smaller term, a more constrained term with more literals. You can get rid of that term with more literals. Right? wz prime is strictly greater than wy prime z prime in terms of the coverage it offers. Right? It's less constrained. So we can get rid of the more constrained term. Right. So here I'm essentially doing some, a very simplified representation by not writing down the full Boolean expression, but just manipulating it in place, right? By adding a term and then getting rid of another term, and then this is probably the most I can do. Right. Actually, after that, after you make use of this additional consensus term, you can also get rid of it. Right. You add it to eliminate another smaller term, and then you can also get rid of this additional consensus term. This one is optional. Right, so you can even come back and throw it away once you make use of it. Right, it's not a very friendly practice, but you can certainly do that. And one thing that is really bothering me is that, in general, there's no way to tell whether you have reached the minimum expression or not. And that is really annoying. You just have to keep eyeballing these expressions until you find something, or until you conclude that nothing can happen. And that's a main challenge we're going to resolve in the coming lectures and coming weeks. Right? A way to really deterministically minimize a Boolean expression to reach the minimum sum of product or product of some forms with minimality guarantee. And we'll see that starting from, I think, the day after tomorrow, or even tomorrow a little bit. Right. Yeah, any questions? Yes, Eric. Yeah, WZ prime is the consensus term between WX and X prime Z. You have X and X prime appearing in those two terms, and then you can pick the remaining variables, W and Z prime, and then combine that into a additional redundant term. Right? And making use of this redundant term to get rid of some of the smaller terms, and then also throw it away once you made use of it. All right. Another hint about one of your workbook questions on Monday, right? To prove that this is not a Boolean algebra. I showed you one valid, four-valid Boolean algebra by filling the table using things like idempotency, identity absorption, complement, commutativity, etc. Right? But this is not a Boolean algebra, and we're trying to find the proof, right? Proving that it's not a Boolean algebra. In general, those are all the axioms and theorems that you can make use of. Right? To prove that something is a Boolean algebra, you need to show that it satisfies all the axioms. To prove that something is not a Boolean algebra, you only need to find one invalid axiom or theorem. Right? As long as you find any contradiction, it is not a Boolean algebra. And I like to sort those axioms and theorems in terms of the difficulty to use them in a Boolean proof. Some of them are very easy to use because they have a very nice visualization in this two-dimensional truth table. Right? For example, you can easily verify commutativity by seeing whether the table is symmetric across this diagonal. You can easily verify idempotency by observing if you have the headers at this diagonal A, B, C, D. Right? You can easily verify identity by looking for this row and column that have the same values as the header, A, B, C, D, A, B, C, D. So the identity element over there is the symbol D. So this one has the identity element of D. The other one has the identity element as A. Identity absorption is also very easy to visualize from this 2D truth table. Right? When you operate something with the identity element of the other operation, you'll get a row of that identity element of the other operation. So A, D, 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 D. Therefore, it also satisfies identity absorption. So quickly, by just visually looking at these tables, you can verify those two axioms and two theorems. Complement is a little bit harder to verify because you need to check for two elements and then in both cardinal maps, in both tables. Right? But that is still doable. Right? What does it mean by complement? Well, A and D, those are the two identity elements of the two operators. They are complement to each other because A and D, A or D, they produce the identity element of the other table, right? The other operator. Generally, we say, A dot A prime equals 0, A plus A prime equals 1. But these zeros and ones, those are the only two elements in two-valued Boolean algebra. But in this four-valued Boolean algebra, you don't have zeros and ones. 0 is really the identity element of the other operator. 1 is really the identity element of the other operator. So when you observe that these two entries are A and D respectively, A and D are complement to each other. Right? The question is, can we find the complement for B, or can we find the complement for C? Right? What I would do is I would just scan through, let's say, this column of the table and this column of the table, and to see if there's some other variable that can be combined with B to produce A over here and D over there. And the answer is no. Right? A and B produce an A over here, but they cannot be complement because this one has to be a D for them to be complement. Right? And then B is not complement to B, C is not complement to B, D is not complement to B because they are not A's. Right? They should be the identity element of the other operation for them to be complements. Right? So B does not have a complement. Therefore, it's not a Boolean algebra. Again, you just have to find a single point of contradiction from any of those axioms or theorems. But complement is a little bit harder to verify compared to the other 4 axioms and theorems, but it's much easier to verify than some of these more complicated axioms and theorems. So when we ask you to verify whether something is a Boolean algebra, I would recommend you to go through those axioms and theorems in that sequence. Right? Starting from the easy ones, try to find a contradiction. If you cannot really find an easy contradiction, you probably have to draw the truth table and then verify distributivity, absorption, and that kind of stuff. Right. There is an additional theorem that you can make use of, which is in Boolean algebra, each element has a unique complement. In 2-value Boolean algebra, 0 and 1 are complement to each other. Right? It's really very easy, very trivial to prove. In multi-value Boolean algebra, like that 4-value Boolean algebra, every element has only a single complement. A has a complement of D, so they sort of form into a pair, right? They are complement to each other. So B and C must be complement. So instead of verifying everything in that B column, right, checking B with A, B with B, B with C, B with D, you only need to check between B and C, and to see if you have an A over here and a D over here. That's actually the only way to construct a valid 4-value Boolean algebra. Right? If not in some of the other isomorphic or equivalent forms, you have to put down A over here and D over there. Right? This is what I showed you last time, the way to construct a 4-value Boolean algebra. Right? And unless you have those values, it is not a Boolean algebra. B and C are not complement to each other. We'll take B and C through the operation. They do not produce the identity element of the other operation. Right? Therefore, B does not have a complement, so it violates one of the axioms of Boolean algebra. And if you really want, you can prove this theorem by assuming that one symbol or one element has 2 complements. And these 2 complements, after going through some of this Boolean algebra manipulation, you can prove that they are the same element, and therefore every element has a unique complement. But don't worry too much about this proof, and even this theorem, you don't have to worry about it. Right? If you really like, you can make use of this theorem in your proof, but it's oftentimes not necessary. Complement, the base form of the complement axiom by itself is sufficient to make most of the proofs. All right, so that's the review I want to give you about Boolean algebra. We went through some of these simplification examples, and then this example about the definition of Boolean algebra and verification of axioms and theorems. Any questions? All right, so let's move on to something more interesting. I know Boolean algebra is usually the boring part of the class, just because you have to deal with so many calculations. Sometimes you don't really know what you're doing. You're just trying to apply some theorems, make it look a little bit shorter. Sometimes you even expand it for the sake of making it shorter. But there's really no concrete optimization objectives. Right? There's no algorithm that can drive that optimization process. So let's keep going with our conversation about Boolean algebra, and then we'll soon see a much better tool. Right? Universal gate. This is also something that we talked about yesterday, where every Boolean function can be represented using SOP or POS. And therefore, if you have access to AND gate, OR gate, and the inverter, you can build any Boolean function. And this is what makes Boolean algebra powerful. to be able to realize any computation by being able to build some universal set. And or not, by definition, that is a universal set. And there's some other combination or set of gates together that allow you to build and or and not. And therefore, those are also equivalent universal sets. NAND gate by itself is a universal set, which means you can use NAND gate, only this one type of gates, to build any Boolean function. And the reason is because we can build not and OR gate using only NAND gates. Right? Sometimes multiple NAND gates, but that is still fine. So you can build an inverter by connecting the same variable to both inputs of the NAND gate, so you get the complement of that variable. Right? So now this NAND gate really behaves like an inverter. You can build an AND gate by inverting the output of a NAND gate. So you put down a NAND gate with X and Y as inputs. You invert it using the inverter you just built. Now you have X and Y. Right? You can build an OR gate by inverting both of the inputs to a NAND gate. And you can verify that by applying De Morgan's theorems to that Boolean expression. So if you have a NAND gate with inverted X and Y, X prime dot Y prime complement, that's the operation of the NAND gate, gives you X plus Y, which is the OR function. So now when you look at this circuitry as only from their input-output interface, right? This is a NOT gate. This one works just like an AND gate. This one works just like an OR gate. And therefore, you can implement any function in a two-level SOP or POS form using a bunch of NAND gates. Right? Even though the number of gates increases, that doesn't detract from the fact that you can implement any function using NAND gates only. And there are many other examples of universal gates or universal set. And the NOT is a universal set because you can essentially build a NAND gate using these two gates. Right? That's like the simplest proof. NAND is universal, so anything that can build NAND is also universal. Right? So and NOT, these two gates, is universal. Or and NOT, they can also be used to build a NAND gate. Or you can also try to build NOT gate, just try to build an AND gate out of these two gates. Right? There are many ways you can make the proof. Once you know the fact that these are already NAND gates, you can use this fact to make some of the other proofs. And in the workbook, we want you to try to prove that XOR and AND also forms a universal set. Right? So for example, I'll get you started. You can build an inverter by just using an XOR gate, sending one of the inputs, and then sending a constant 1 on the other side. And this gives you an X prime. Now you have an inverter built out of the XOR gate. Right? And you just AND gate is ready here. And the only thing left for you to prove is to build an OR gate out of these two gates. Right? That proof is even optional because we already told you that AND and inverter, that is a universal set. So once you build an inverter and AND gives you a universal set. Yes?
What is the second input?
The second input is a constant 1. Yeah. So 1 XOR 0 gives you 0. 1 XOR 0 gives you 1. 1 XOR 1 gives you 0. So the output is the complement of that changing input. There are also some examples that are not universal set. For example, with a single AND gate, you just cannot do inversion. There is no way for you to go from 1 to 0 and 0 to 1. And similarly, XOR allows you to do inversion, but it does not allow you to build AND or OR gates. So we're just seeing this proof for a NAND gate. Again, this is a formal proof to build all three gates using some different gates or some different set of gates. And universal gate is an important concept for, I would say, two reasons. So for one thing, whenever you develop a new technology for anything, for any kind of computation, you need to verify that you can build a universal set so that you can realize any computation. And that is what people did when they started to develop quantum computing. They try to build AND and inverter using quantum devices, right, to make sure that quantum computer can realize any computation that traditional computer can do. And you only need to build these two simple gates to make that proof. These are universal sets, so they can be used to implement any computation. Right? It's also true for some of the other newer technologies, like near memory computing. and also new fabrication technologies. When someone proposes a new technology, like 3 nanometer, 4 nanometer, or different kind of devices, different kinds of material, they need to verify that they can build at least a universal set to make it work, right? To be able to build general purpose computers. And also, people apply this kind of ideas, analysis of universal set when they develop things like privacy preserving computing. Have you heard about it? Multi-party computation, homomorphic encryption. Right? It's essentially a way for us to do some computation without leaking our secret. So let's say Eric and I, we're going to see who has more money in the bank. But of course, we don't want to share with each other how many money we have. We have 2 choices. Number 1 is to find a third party that we trust, right? Like a banker or maybe a good classmate of ours. Or we can go through some of these security-preserving computation protocol to make this computation happen between ourselves, but still without leaking our sensitive data. And over there, any of the computation is modeled as a Boolean circuit. And at least you need some universal set. They're typically modeled in terms of AND and XOR, which is indeed the universal set, right? The one that you're going to prove in your workbook. It is only with this kind of characteristics that we can easily verify the feasibility of a new technology. Right? Instead of implementing everything, we just need to implement 2 gates to prove that this is a universally applicable technology. The other thing is chip fabrication is a very expensive process. You need to go through design, verification, and fabrication. Right? The fabrication involves those $1 million devices, and then to fabricate all the devices at that nanometer scale. You have billions of transistors nowadays, and the wires will run like more than 1 mile in that tiny little chip. And we need to make sure that everything works properly, and it just doesn't happen. There will always be some manufacturing defects. Right? For every, let's say, 100 chips you manufacture, probably only 80 of them work fine, and the other ones do not work. And over there, what you can do is you can reserve a trunk of NAND gates. NAND gate is a universal set, so you can use that to implement any additional functionality as you like. And therefore, you can rescue those malfunctioning chips by repurposing this NAND gate to that failure part, and therefore still realize the correct computation. And you can also use NAND gate to modify the design at a very late stage of the design process. Right? Once someone else has already spent hundreds or thousands of hours in verification, in developing testing plan, you can repurpose NAND gates to only locally modify the circuit without changing the overall blueprint. And that will make the verification job a lot easier. Right. So again, universal set is a quite important engineering principle for not just circuit design, but also fabrication and some of the other computer science-related problems. Right, when it comes to exploring new technology. Right. The next gate I want to show you is an XOR gate. We already saw this when we deal with error correction codes. Right, that Hamming code is constructed using a bunch of XOR gates. Here we're just having a more formal look at this gate. So XOR, for 2-input XOR, you can think of this as an inequality gate, which means the output will be 1 when the inputs are different. 0, 1, 1, 0, those are the input combinations, producing a 1 output at the end of the XOR gate. You can also build a multi-input XOR gate. So you draw an XOR symbol, you connect as many inputs as you like to that gate. And in this scenario, XOR will behave as a parity gate, which means it will produce an output of 1 when you have an odd number of 1s at the inputs. Odd number of 1s at the inputs. Right? That is also true for this 2-input XOR gate. You have an odd number of 1s at the inputs, output is 1, but you can also generalize the same idea to a multi-input XOR gate. And the expression at the bottom is how we expand an XOR gate or XOR symbol into some sum of products or product sum expansions. So the output is 1 when x is 0 and y is 1, or when x is 1, y is 0. And you can apply distributivity to get a product of sum expression for the XOR gate. You need this kind of expression. If I give you a Boolean expression with XOR and ask you for the minimum two-level sum of products, you probably have to expand it into sum of product first, and then applying the regular Boolean algebra, or the axioms and theorems to make that simplification. Right. XOR has a little bit more theorems. When you deal with XOR and a constant, we essentially use this theorem to prove that we can build an inverter from an XOR gate. Right? X XOR X, 0, 0, 1, 1, they all produce an output of 0. X XOR its complement, produce a 1. 0, 1, 1, 0, produce a 1. XOR is also commutative. Right? This table, that table is symmetric. So the gate itself is commutative. It's also associative. Multiple levels of XOR, you can shuffle the order of the inputs. Essentially, just checking the parity of all the inputs. So the input order doesn't really matter. Distributive. This is one thing that Eric raised in the last lecture. XOR is sort of distributive. It's not fully distributive because the other side of distributivity doesn't work. But this particular one does work. And we'll see that in 1 second, why it works. And finally, XOR. Since it's a parity gate, when you complement this overall behavior, it's no different from just complementing one of your input variables, which changes the parity by 1, right? Odd to even, even to odd. And you can also write it out as a sum of products expression. Essentially, the opposite of the original two-dimensional truth table. When x, y are 0, 0, and 1, 1, represented by those two product terms, the output of an XOR is a 1. Sorry, XOR complement is a 1. Remember one of the principles we learned about Boolean algebra, the duality? Right? I would say everything in this class has two sides. When you have sum of products, you have product of sums. Right? When you have that one side of the theorem, you have the other side of the theorem. And when we see XOR, when we see AND gate, we see NAND gate. When we see OR gate, we see NOR gate. And when we see XOR, there's also, of course, an XNOR gate, the opposite of XOR. Right? Just flipping the values from 0 to 1 and 1 to 0. So now this can be called an equality gate. When the two inputs are the same, 0, 0, 1, 1, output is a 1. And here are all the Boolean expressions, two-level SOP or POS, and how you convert between XOR and XNOR. Right? Complement is forcing or complement one variable. It's the same as flipping the parity. So you get an XNOR after you do any kind of single flip. Right? At the operation, at the input variable, or at the output. Right? As long as you flip one thing, you change the parity. So you go from XOR to XNOR. Right? So here's an exercise for you. I want you to try it out to algebraically prove that this distributivity is true. Right? Applying Boolean algebra. Again, to use Boolean algebra, all of the axioms and theorems, those are defined in terms of OR and AND functions. Right? So the first thing is to convert the expression into some AND/OR expression. I'm going to put you the XOR theorem on the side just for your reference. X XOR z is the same as, sorry, y XOR z is the same yz prime plus y prime z. I think this is all you need to make the proof. I'll give you 2 minutes to work on this proof. Right, just try to do that XOR to AND/OR conversion first, and then apply Boolean algebra to make two sides equivalent. If anyone has some questions, just raise your hands and then I can come over to you to give you some help. We have another 30 seconds. Yeah, anyone got a proof? Does anyone got a proof already? If not, I'll give you a bit more time. Eric, yeah, you got it?
I don't know.
What is this xy prime, xc prime?
Because
Yeah, I think that's an XNOR, like part of XNOR expansion, not quite the XOR. Qing, you got a proof? Yeah, I think that's a very nice, very elegant proof. Yes, Manis. Okay. What about this? Let's talk with people around you. Check with each other your work and see, if you can help each other complete the proof. And Max, I guess you can get together with Aishwarya. Then try to find a neighbor and then do a little bit of talking.
Yeah, I'm just kind of confused. Like, I
Yep.
treated this as y and z.
That's right.
Okay, and then am I allowed to use the other theorems?
Yes, you are.
Like this?
Yes.
Okay, so I would just work down and then make it look like this in the end.
That's right. But the first step is you're trying to complement this xc by putting down two complement symbols. Right? But that's not quite right because we have De Morgan's law. Xz complement is x prime. You also have to switch the operation. Okay. It's not the product between them, it's the sum between them. So what you should really have is xy times x prime plus z prime as your first term.
Oh, I see. So this is incorrect.
Yes.
Oh, okay.
Yeah.
Okay. Quick,
Yeah.
When you said the exclusive that.
By parity, I mean it's checking for odd and even. And this one is, you can call this an odd parity. Output is one when you have an odd number of ones at the inputs.
Oh, okay. So if it's odd, it's 1. If it's even,
Yes.
have an output as 0.
Yes.
Okay. Okay. Thank you.
Mitchell, you look to be stuck somewhere.
oh, I didn't practice yet, so
I see.
I gotta catch up on my shoes.
All right. Max, what did you get? You're only like one step away. All right. Let's do this together. The idea is to first apply these XOR theorems and then apply the regular Boolean theorems until the left-hand side and right-hand side converge. Right. So what I can do is I'll just follow first the XOR theorem to expand it, all the XOR into some corresponding and or representation. Right, so this will be x times y XOR z, as I wrote on the top right, yz prime plus y prime z. Right, I'm going to start with the left-hand side first. Right, I'll probably just simplify this all the way down to a minimum 2-level SOP and then compare the two sides from that SOP expression. Right, otherwise, I probably don't know in which direction I should simplify towards. SOP is like a fixed target. And you can simplify, convert both sides into an SOP, and then make a comparison over there. And this is x, y, z prime plus x, y prime z. Right? This is already minimal. Right? Quite easy to get the left-hand side into an SOP. So the right-hand side would be, again, according to the formula, you treat this as a single expression, xz as a single like variable expression, and then apply the XOR. And that will give you xy times xz complement plus xy complement times xz. And now we apply De Morgan to that complemented expression. Xy times x prime plus z prime plus x prime plus y prime plus, times xz. And now it's only to apply distributivity. Right? Some of these things I know, you have x and x prime, and they will multiply to 0. So that term will disappear. I don't even have to write it out. I will only combine xy with z prime to give me xy z prime. Similarly, on the right-hand side, x prime and x, when you apply distributivity, that will cancel out to a 0. So you can ignore that. And then whatever left, it will be x, y prime z. Right now, left-hand side and right-hand side are equivalent. Right, the way we compare those two XOR expressions is to convert both of them to an SOP, and then make a comparison at its more comfortable two-level sum of product expression. All right, and XOR and XNOR. Do you think these two expressions are the same or different, like opposite to each other? Okay. Give you 10 seconds, and then I want you to show me your hands. 10, 9, 8. Are they the same or opposite to each other? All right. Who thinks they are the same? I think we have a few hands, so the rest of people think they're different. Any reason why you think that's the same? Any explanations? Intuition? All right, we know that for two level, they're the opposite. For two input, they're opposite. Right? A XOR B is the opposite of A XNOR B. Right? By definition. These three input XOR and XNOR, they're actually the same. And we can show that using some of the XOR theorems. The bottom one will be the same as A prime XOR, sorry, I'll find the easy route. So A XOR B prime XNOR C. Right? Essentially, I'm putting down parentheses over here, and then I'm applying one of the XOR theorems. Flipping the operation is the same as flipping one of the input variables. And then I'll just do some regrouping. B prime XNOR C, which gives me A XOR B XOR C. Right, so the three input XOR and XNOR are the same. Right, so They're different. They're the same. What about that 4-input XOR and XNOR? Right? If you were to take a guess, you'll probably say they're different. Because there's something related to parity, odd and even number. And then we have this kind of different behavior between 2 and 3 input, XOR and XNOR. And indeed, that 4 input, they'll be the opposite to each other. Right, this is the annoying thing about XNOR. XOR, you can describe it very nicely as an odd parity gate. Odd number of ones, output is 1. For XNOR, you just don't get such a perfect description. Right? Its behavior alternates between odd parity and even parity when you have more and more inputs. And that's the reason why we use XOR in the error correction equation. That's a more well-defined behavior. And that's also the reason why you have that workbook question when you replace XOR in the correction equation, which involves 4 variables. Right? Change it to XNOR, you get the opposite. Right? So here's the more fine-grained reasoning for that analysis. Right. So what we have so far are 2 quite powerful tools. Number 1 is truth table. You can use truth table to prove the equivalence of 2 functions by just fully expanding out all the input combinations and then enumerating the outputs. You can use truth table to prove also non-equivalence. Right? If 2 columns look different, they are not equivalent. The other powerful tool is Boolean algebra. You can use that to do simplification. Convert a large expression to a smaller one. Convert an XOR expression to an AND/OR based expression. You can also use that to prove equivalence. Right? Left-hand side, through a sequence of transformation, arrives at your right-hand side. Right? But the drawback is that sometimes it's hard to just eyeball the by simplification steps. Right? For truth table, the size grows exponentially with the number of input variables. And so these problems are kind of bothering us. But trust me, we're going to see a solution pretty soon. Right. So with that, I'm going to move on to the next topic, Minterms and Maxterms. All right. So starting with a design example. So this is a 3-bit 011 comparator. You have 3 input bits, and when the magnitude is greater than or equal to 011, output is 1. Right? That's how we convert a behavior description into the truth table and later on into a circuit implementation. To represent this function, we can essentially, well, one thing is the beginning point would be you pick up all these conditions that produce a 1 and then describe them in terms of some product terms. So f will produce an output of 1 if your input is 0, 1, 1, so A prime B C, or your input is 1, 0, 0, A B prime C prime, or it's 1, 0, 1, A B prime C, etc., etc. Right? Collecting all these conditions that produce an output of 1 and then OR them together. If your input pattern satisfies any of these, right, any of them, so that's through an OR operation, output is a 1. And that expression can be further simplified by applying the uniting theorem, uniting again, and finally applying literal elimination to get a minimal SOP expression. Right. What we're doing at the top, those 5 terms, the 5 products, describing each individual condition producing a 1, those are called a collection of minterms. A minterm of n variable is a product of n literals in which each variable appears exactly once in either true or complementing form. That's a complicated description. So a minterm is just a product of all the input variables. Some of them could be inverted, and some of them are non-inverted. Right? So these are like, precisely speaking, how we differentiate variable, literal, and minterm. Variable are the inputs to our circuits, so ABC. Literal is variable appearing in either non-complemented form or complemented form. So you would have 6 possible literals for this 3 input function. And the number of minterms would be 2 to the power of n. Every input combination can potentially be translated into a minterm. Right? So 0, 0, 0 would be described as when A is false, B is false, C is false, you want that to produce a 1. Right? So describe it as A prime, B prime, C prime. Similarly, 1, 0, 1, you describe it as A is true, C is true, B is false, you want that to produce a 1, so A, B prime, C. With these minterm representations, to implement a Boolean function from a truth table, it's simply a task of collecting all the minterms. We look at all the rows where the output produces a 1, and then we write out the corresponding minterms, like AB, A prime, B, C, A, B prime, C prime, etc., including all the minterms in a sum function, in an OR gate, to implement that overall function. And this minterm, this is called minterm expansion. a collection of minterms representing functions. And minterm expansion can be represented in a few different ways. You can represent that using the regular Boolean expression form, sum of minterms or of minterms. You can represent that in terms of the indices of these minterms. So minterms are sorted between 0 and 1, depending on just this binary number. Right? If it's 1, 0, 0, we call that a minterm 4. In binary, this is 4. 1, 1, 0, in binary, that's 6. So we call the corresponding term minterm number 6. So minterm expansion can be represented also as a collection of indices, right? Using either this fully expanded M3, M4, M5, or in that sigma notation. Sigma indicating a summation, right? A sum of minterms at index 3, 4, 5, 6, 7. That's how we can describe any function using a collection of minterms. And this is a canonical form. So canonical means the representation is unique and complete. You can represent any function using a minterm expansion, and there's only a unique representation. Right? Just specifying whenever you have a 1, you have to sort of specify minterm number 3, and there's no alternative. Right? You have a unique and complete representation. So it's called a canonical form. Any questions about how we convert the truth table into a collection of minterms and then convert that into a Boolean expression? All right. And because of this duality stuff, if there's a minterm, we also have a maxterm. And maxterm is like the opposite of minterm. Minterm uses products to describe ones in your function. Maxterm using sum terms to describe zeros in your function. Again, 3 variables, you have 6 possible literals, and there could be 2 to the n, so 2 to the 3, 8 different maxterms. Each maxterm is a sum term, a summation of some literals. But one thing worth noting is that for the maxterm representation, the kind of variable, the literals are flipped compared to a minterm representation. So for minterm 0, we describe it as A prime, B prime, C prime. For maxterm 0, we describe it as non-complemented A plus non-complemented B plus non-complemented C. And that is actually the opposite of the minterm. If you take the complement of these products, you would get A plus B plus C. So minterm and maxterm are complement to each other. Right? But now when you call maxterm 0, that will translate into that product in the sum term with non-complemented literals. And maxterm, again, we can use a collection of maxterms to describe any Boolean function by looking for all the input combinations, producing a 0 output, and then take the product of the maxterms. Right? Each maxterm is a sum term. When we take a product, we'll have a product of sum expression, right? POS. Or more specifically, in this case, product of maxterms. You can represent that as a Boolean expression. You can represent that as the indices for the maxterms. Those are completely equivalent representations. You can freely convert between the two. Right. Again, for minterms, you look for all the rows producing output of 1, collecting all the minterms through an OR gate. For maxterms, you look for all the input combinations producing an output of 0, and then collecting the maxterms through an AND gate. That allows you to convert any truth table into a canonical 2-level SOP or POS representation. Any questions so far? All right. So these things are called minterms and maxterms for some obvious reasons. Minterms gives a 1 for just one combination of input variables. Right? A plus A prime, B prime, C prime, you look at it as a Boolean function. Produce a 1 only when your inputs equals 0, 0, 0. Right? It is on for a minimum non-trivial amount of possibilities. There's only one thing that can make it a 1. So it's like minimum. Maxterm gives a false value for just one combination of input variables. But conversely, it is true for the maximum non-trivial amount of possibilities. As long as your input is not 0, 0, 0, this will be a 1. Right? So it's like the maximum representation covering a lot of 1s in the function. So again, that function, the truth table, can be represented as a minterm expansion or maxterm expansion. And these two better be the same, since they're describing the same function. Right? They have to be the same. Otherwise, there's some mistake. And we can prove their equivalence. Again, we have two different tools, truth table or Boolean algebra. Right? Truth table, you just enumerate all the conditions. And this is indeed what you should get for both functions. But let me also approach it in the algebraic way. Again, one thing, the first thing I noticed that I have this a plus b shared in common. So I'll factor it out to simplify my simplification step. Plus c dot c prime. A plus b prime plus c. Right? This is a non-intuitive way of applying distributivity, the one that is not valid in ordinary algebra. Right? But this is valid in Boolean algebra. So c prime disappears. And now what I'm left with is something that I can apply term elimination, because I see a that is in common between the two terms. So I can sort of ignore it, but I also see b and b prime, which allows me to get rid of b prime. Does it make sense? So you can write it out as a plus b times a plus c. Right? I'm skipping, again, like 2 steps in the middle. Right? Really, we're applying first distributivity, followed by term elimination, and then followed by distributivity again. Right? And if you want to convert this into a 2-level sum of products, which is getting a little bit closer to the top expression, so that's probably what we want. You can write it as a plus just bc. Right? It's really a plus ac plus ab, but ac and ab, those are absorbed by the single literal a. So this is the minimal 2-level SOP expression. And at this point, I just hope that the top one is equivalent to this expression. So the top one, right? First, I have these 4 terms. All of them have a in common. And they take BC as 0, 0, 0, 1, 1, 0, 1, 1. And those 4 terms, through two steps of uniting, can be converted into just a. And then through term elimination, I can get rid of a prime. So I get a plus bc. And now I just proved that minterm expansion and maxterm expansion are equivalent. All right. Any questions so far? Right? We're seeing a new concept, minterm and maxterms, but we're connecting it sort of back to what we have already learned through Boolean algebra, and to prove that this really matches exactly what we learned earlier. And they should match, since they all operate under the same Boolean algebra framework. And then I'm just going to take you to a few more revisits to connect the concepts between gates, Boolean algebra, with this new thing, minterm and maxterm. That's the truth table, or the 2-dimensional truth table for a NAND gate. Right? NAND gate is AND inverted. And if you apply De Morgan, this is what you get, x prime plus y prime, right? After De Morgan application. And that is the sum. It's the sum of two literals. And that corresponds to exactly the max term at 1, 1. So the sum term, the same as the max term at 1, 1. Right? For NOR, again, that's the complement of OR. And when you apply De Morgan, x prime, y prime, this product is exactly the minterm at 0, 0. Which means these gates do make sense in terms of the minterm maxterm look versus their functional definition. XOR and XNOR. XOR can be expanded in this form, right, as we saw from that XOR theorem. And they correspond to 2 minterms, 0, 1, and 1, 0. Right. XOR can also be represented using that expansion. Also, that's part of the XOR theorem. And these two, this is your max term number 0, 1, 2, 3. And this is your Maxterm number 0, which are exactly the two Maxterms in the 2D truth table. Again, these XOR theorems, you don't have to remember them. Those are trivial truths from the Minterm and Maxterm expansion. And now again, I told you that XNOR is the complement of XOR for these two input gates. Therefore, if you try to complement the Minterm view of an XOR function by taking the Minterm expansion and then complementing it, and then applying the Morgan's law, this is what you get. And that is actually the Maxterm definition of an XNOR gate. So this term, x plus y prime, what is the Maxterm index for that sum term? What is the index of the Maxterm? That is Maxterm number 1. This one is Maxterm number 2, which are Maxterm number 1 and Maxterm number 2, respectively. Again, when we apply this Boolean algebraic transformation by inverting the XOR expression, we do get a valid, a reasonable Maxterm expansion of the XNOR gate. Right. Similarly, if you take the Maxterm expansion of XOR, you complement it, this is what you get after applying De Morgan. And this is exactly a Minterm expansion at 0, 0, Minterm 0, and 1, 1, Minterm number 3. Right? And that is, again, the definition of XNOR. So even though Minterm and Maxterm is a new concept in this lecture, it's really the same as what we have seen earlier, right, from Boolean algebra, from the definition of XOR and XNOR. Yeah. Any questions? Right. In general, I would say people are more comfortable with dealing with Minterms because, like x, y, you can look at it as a 1, 1. So 1, 1 corresponds to Minterm 1, 1, so Minterm number 3. Right. But for Maxterm, a bit of inversion is happening. You have to look at this as x equals 0, y equals 1. Right. So that's Maxterm 1, 0. So it's Maxterm 0 and 1. So that's Maxterm number 1. So a bit of inversion is happening for Maxterm, for product sums. So people tend to be less comfortable with dealing with those representations. Right? But we all work with the kind of more positive side of the equation, the sum of products, the Minterm more often than Maxterm. But be sure you're also comfortable with, with a bit of more time invested, being able to handle Maxterms and product of sums. All right. So that's all about XOR and XNOR and their correlation with Minterm and Maxterms. Now we're going to move on to a different topic, which is called incompletely specified functions. All the truth tables we have seen so far are completely specified. For every input combination, I'm defining the output to be either 0 and 1. Right? But in realistic systems, let's say you're trying to design this function, but this function has inputs from other sources. Right? The inputs could come from another function, could from some input constraints, could come from some system specification. And in those scenarios, you have a constrained input space. And not all input patterns may appear. Right? So for example, if you're designing a vending machine, there's a button on the left and a button on the right. It's just not physically possible to press both buttons at the same time. So that's a condition that should never happen. And that's called a don't care conditions. Right? We just don't care that condition because we know it's never going to happen. And in terms of truth table representation, we show them as an x at the output column. Right? So now you have 3 values you can put in the output column, 0, 1, like before, and also x, meaning that that input combination will never happen. Do you think this is good or bad? Say that again? Why is it bad? Just feeling. Yeah, Judy.
think of some case.
Yeah. So I think Judy brought up 2 important points. For one thing, we can put them as either 0 and 1, right? If they are truly don't cares. And we can actually choose 0 and 1 so that we can get the maximum minimization out of it. Right? Whichever assignment that gives me more room for optimization, I'm going to go with that. Right? So it's probably good for optimization purposes. You have more flexibility. Right? There's a situation you don't have to worry about. And then you have full flexibility of setting them to whatever you like. Whatever one that gives you a smaller expression. But in the meantime, you have to make sure that they truly never happen. And if they ever happen, it's going to be quite problematic. The system is going to run into some, well, they will eventually receive some values, 0 and 1, based on how you design the Boolean circuits. But that is out of our control. Right? We just didn't really force it to operate in a particular way. So it could be dangerous for some security-sensitive systems. And this morning, I was parking at the Gilman structure. And there's a Triton commuter club. Does anyone? Did you enroll in that club?
No, but I
Yeah,
know.
they have a bunch of. They have commuter lounge. They have for me, they have a promotion where you take public transit for a few days. You can get some points, and you can redeem those points for a parking coupon. Give you 50% off. So typically for me, a B parking is $6, and the coupon makes it $3. But as I'm getting more points, I eventually clipped multiple coupons and loaded all of them to my parking accounts in Park Mobile. But I think there's some incompletely specified conditions that they didn't handle. When you have multiple coupons, they overlap. You can use both of them in one transaction, which makes parking free. I think that is unintended. It's supposed to be used 1 coupon per day, and then with 2 coupons, you can use them for 2 separate days. But as it turns out, you can use 2 coupons on one day to get 100% off your parking. I would say that's an incomplete specified condition at some point. Probably before that, many months or many years ago, you can now put 2 coupons in your account. Right? Coupon might be associated with transactions, so every time you have to type in a coupon. But when they added a new feature later on, right, to be able to save coupons in your account, the more corner cases could arise. So in that case, handling all the conditions beforehand would be good. Right? It gives you better reliability, security, and predictability. But in this class, we care more about minimization. So let's assume that these don't cares are truly don't cares. Right? They are guaranteed to never appear. And we get that guarantee from system specification or from the output behavior of the other module. Right? In that situation, we can make use of them to optimize our circuits. So I'm going to remind you about this overtaking example. We have a vehicle ahead of us. Left zone, right zone, you need to detect whether there's any vehicles in those regions before you make the overtaking decision. And you essentially only overtake when the car ahead of you is driving slowly, and at least one of these is empty. Right? That's what allows you to overtake. And I think our discussion with Mitchell when he showed the truth table on the board over here, I said that 100 case, you can handle that in many different ways. Right? 100 means the vehicle ahead of you is slow, but both regions are open. Right? So you can either choose to overtake on the left or overtake on the right. And depending on whether there's another system to handle that behavior, if you generate 1-1, right, overtaking intention on both sides, then there has to be another module to handle that decision. But let's say here we make a different choice. We just let it overtake on the left, right? Which is usually a more kind behavior in this driving environments and in many countries. You're encouraged to overtake on the left. So let's say we overtake on the left. So now, if the output of this module is sent to the next function, right? On the next function, 1-1 will never appear. Right? So 1-1 would be a don't care condition for the next module receiving the output of this function. So this function produces 0, 1, 0, 0, 1, gets sent to the next function. When I design the next function, 1-1 becomes a don't care condition. So let's say that is our planning module. And the planning module will control many other modules, the steering module, right? When to turn the steering wheel, and the acceleration module, right? Accelerate or brake. And part of this acceleration module could be a pre-acceleration module. Once you receive the intention, you might not want to execute it right away. but you want to get your system ready for execution whenever that execution command comes in. So that pre-acceleration module is going to monitor the intention to overtake. And whenever there's an intention, it will set up everything, the gearbox, the energy chain, the ABS, get everything ready for immediate reaction. Right? So it receives the inputs from the planning module, overtake on the left, overtake on the right, that is the intention. And then it will produce a 1-bit output indicating that whether I want to get everything ready or no, I'm just driving normally. So let's say if there's no overtaking intention, right, I don't have to get those systems up and ready. So I can just let it on the standby mode. Sorry, I mean, just let it in the kind of like the break mode, like not doing anything, right? Continuing what it was doing before. But if there's an overtaking intention, whether it's on the right or on the left, I want to put all of these components of the vehicle onto the standby mode, right? Ready for immediate reaction. And 1-1 is something that, based on my previous functional design, 1-1 will never happen. I already did the tie breaking in that previous module. So 1-1 is a case that will never happen. Right? That's how we show this kind of behavior in a truth table. So we have a choice. This x can be used as a 0, can be used as a 1. Right? Both of them will be equally valid, assuming that 1-1 never happens. But they will lead to different implementations. If we make it a 0, you can implement this logic using an XOR gate. 0, 1, 1, 0 produce an output of 1. So this function can be implemented as an XOR gate. If I make it a 1, that is the truth table for an OR gate. So you get an OR gate implementation. These are two different implementations. And in fact, OR gate is, in terms of semiconductor implementation, is cheaper than XOR. OR gate requires 6 transistors. XOR requires 80. Right? So that might be the preferred method if we're actually implementing this using transistor devices. And this is only a very simple example showing that you get different implementations. In general, this implementation could have drastically different implementation costs. So if I will come back to this previous example on incompletely specified functions, right, the first example I showed you at the beginning, you could actually implement this using a single gate. And it looks like a pretty complex function with ones spread it out all over the place. But you can eventually implement that using a single gate. Does anyone know which gate we can use? Again, no perfect solution. It's just like an eyeballing exercise. If you just happen to be lucky, you can probably see that gate right away. All right. So I'll show you. So the function will produce a 1 when B and C are 0, 0, 0, 0, and 1, 1. And this 1, 1 is like a don't care case. Right? So I could say that whenever B and C are the same, when B equals C, I let my output to be a 1. And that is an XNOR gate between B and C. The equality gate producing the output function. So lowercase b and c as the inputs. How do I know that? Well, just trying many things, and then it's probably what I observed. But again, in general, there's no systematic method you can apply to find such a minimal expression. But we're going to see the systematic method in another few lectures. And finally, there's just one last thing I want to bring up to your attention, which is you can also represent those don't cares in this Minterm and Maxterm expansion by additionally including a summation of letter D representing don't cares, and then find out the indices of those don't cares. So that truth table and these expansions are equivalent. So with that, so here's where we are. We are talking about design, analysis, and optimization of combinational circuits by manipulating Boolean algebra. We have seen a few powerful tools: Boolean algebra, truth table, Venn diagram, circuit diagrams. Those are the tools you can use to manipulate and simplify Boolean expressions. And then we're going to see more tools in the coming lectures. So this is everything for today. We covered a review of Boolean algebra. We covered minterms and maxterms. And finally, we talked about how to handle incompletely specified functions. Giving them different assignments and then exploring a larger design space, hoping to get the best. Yeah. Thank you. Yeah, and if anyone is looking for a workbook partner, feel free to talk to people around you. I saw that not many people formed into groups.